Okay, so now all of you please concentrate. So this is the bridge rectifier circuit and we are going to discuss about it. So we have to see that the circuit diagram, then working of this bridge rectifier circuit and its a waveform. Okay, so see that I think in the previous session I have already explained the how the circuit diagram of a bridge rectifier circuit it can be remembered. If you observe the circuit diagram here in the bridge rectifier circuit, the first one is the center tap transformer is not required. Have you observed that? It's an ordinary transformer is used here. It means that the drawback of center tap fluid rectifier circuit it overcome here. This is a normal transformer here. Now, as we know that the primary winding of a transformer is connected to AC supply, and the secondary winding, the voltage developed in the secondary winding, which is called as a input voltage to the rectifier circuit. So that's why the voltage in between the terminal A and B, we call it the input voltage. And now in between these two terminals, the bridge circuit is connected. If you observe that diode D1, D2, D3, and D4, they are acts as a bridge circuit, and in between the two opposite corners, the point A and B is connected, and in between that another opposite corners, the load resistors RL is connected. And you know that output voltage is always measured in between or across the load resistors RL. And now let's we consider that this is our input voltage waveform, which is measured in between the point A and B. Is it right? So that the input voltage waveform is always sinusoidal. If I want to draw that input voltage waveform, which is measured in between the point A and B, and that input voltage waveform is always sinusoidal. So when I want to discuss the working of the bridge rectifier circuit, we always discuss in two parts. One is for positive half cycle and another one is for negative half cycle. Now, for every positive half cycle, point A acts as a positive terminal and point B acts as a negative terminal. Is it right? Now see that, as you know that the current always starts its journey from positive terminal, means the current it starts from the point A. Is it right? Now when it comes at this point, now you can observe that the positive terminal point A is connected to the P region of diode D1. It means that the diode D1 works in a forward bias, but it is connected to the N region. So may I say that the diode D4 it works in a reverse bias, so that I can make it circle around it. Similarly, as you know that the point B acts as a negative terminal, so if you observe that the negative terminal is connected to the N region of diode D3, means diode D3 works in a forward bias. But as this B point is connected to the positive or P region of diode D2, so may I say here the diode D2 it works in a reverse bias. Now if you actually observe the picture here, then you can see that for positive half cycle, diode D1 and diode D3 is in a forward bias, and diode D2 and D4 are in reverse bias. So how the current it will flow? So definitely the current it can flow. It starts from point A, it comes to this point. It will not take the path of a diode D4. Whole current will take a path of a diode D1. Then when it comes to this point, definitely it will not take the path of a diode D2 because it acts in a reverse bias. Whole current will take the path of a RL, so that RL will get its polarity. And then when it comes to this point, it will take the path of a diode D3 and then it return to the negative terminal. So in this way, this is the direction of a current here. Get it my point? So that in every positive half cycle, I say that the current it flows, and for positive half cycle, the diode D1 and diode D3 works in a forward bias, so that we will get the output same like a input waveform is there. So this is the output is there. Get it, my point? Means for every positive half cycle, diode D1 and a diode D3 acts in a forward bias, and you will get that output across the load resistors RA. Here we always measure that output here. Get it, my point? And now see that what happened for every negative half cycle. Let me remove this point. Now for the negative half cycle, the polarities get reversed. It means that point A acts as a now negative and point B acts as a positive. Now when point B acts as a positive terminal, now you can see that when it is acts as a positive terminal, it is going to be connected to the P region of diode D2. It means that diode D2 now it is in forward condition, but as it is connected to the bar, it means that N region, so that diode D3 works in a reverse bias. So let me make it circle around it. Now point A acts as a negative. Now you can see that this is a negative A point, which is connected to the N region of diode D4. It means that diode D4 acts in a forward bias, but it is connected to the P region of diode D2, means I say that diode D1 acts in a reverse bias. So now if you observe that for every negative half cycle, diode D1 and diode D3 acts in a reverse bias, and diode D2 and D4 acts in a forward bias. So that if you see that how the current it is actually flow in the bridge rectifier circuit, so now you can observe that current it starts its journey from positive terminal, means point B, it comes to this point. Definitely this current will not take the path of a diode D3. The current will take the path of a diode D2. Now that point, the current it comes here. Now again, the current will not take the path of a diode D1 as it is work in a reverse bias. So entire current will take a path of a RL, and based on that RL, you will get that the polarity. Now when the current it comes here, it will take a path of a diode D4 and it will return to the negative terminal here. So this is the direction of a current flow here. Get it, my point? So if you see that the output voltage developed across that RL, in both the cases, the polarity is not changed. And as the RL polarity is not changed during the positive half cycle as well as during the negative half cycle, it means that the voltage developed across that RL is in a unidirectional. म्हणजे जर पोलॅरिटी जर RL ची पॉझिटिव्ह हाफ सायकलला आणि निगेटिव्ह हाफ सायकलला जर चेंज होत नसेल, तर त्याच्या अक्रॉस जनरेट होणारं जे काही व्होल्टेज असेल, so that voltage will be generated in a one direction, and that direction is nothing but in a positive direction. So that the output voltage across this RL during that entire cycle will becomes like this. You can observe here. For positive half cycle, let me write it down here. For positive half cycle, the diode D1 and diode D3 acts in a forward bias, and for negative half cycle, diode D2 and diode D4 acts in a forward bias. So in this way, for every positive half cycle, output is available due to the diode D1 and D3, and for every negative half cycle, the output is available due to the diode D2 and D4 is there. And now, if you see this output waveform, if you see this output waveform, it is clear that this output waveform is not pure DC signal. It means that whatever the output is available in the bridge rectifier circuit, that output we call it's a pulsed DC output. Pulsed DC output is there. It means that it contains AC as well as DC component. And now, if you observe that the output waveform of a bridge rectifier circuit, and if you compare this output waveform with a center tap full wave rectifier circuit, center tap full wave rectifier circuit, does it is the difference between these both the waveform? Definitely no. The output waveform of a center tap full wave rectifier circuit is exactly same as the bridge rectifier circuit is there. It means that then what is the difference between the center tap full wave and the bridge rectifier circuit? The only one difference is that the transformer. In the center tap full wave rectifier circuit, the center tap transformer is required, and in the bridge rectifier circuit, ordinary transformer is required, not a center tap transformer is required. Other than that, the rest of the things is the same for center tap full wave rectifier circuit and the bridge rectifier circuit is there. Another one difference in between the center tap and the full wave rectifier circuit is, in a center tap full wave rectifier circuit, two PN junction diodes are used, and in a bridge rectifier circuit, four PN junction diodes are used here. So this is the difference between the center tap full wave rectifier circuit and the bridge rectifier circuit is there. But now, if you try to remember the output waveform of a half wave rectifier circuit, output waveform of a center tap full wave rectifier circuit, and now you can see that the output waveform of a bridge rectifier circuit. So you can say that the common drawback of all type of a rectifier circuit is that the output of all rectifier circuit is a pulsed DC output. We will not get a pure DC signal as an output of any type of a rectifier circuit here. It means that output of a full any type of a rectifier circuit is a pulsed DC signal. It means that output it contains AC as well as DC component. Get it my point? And again, if you observe that, as we say that the output waveform of a bridge rectifier circuit is the same as the output waveform of a center tap full wave rectifier circuit. So may I say here, output frequency of a bridge rectifier circuit is 2 times of input frequencies there, as we already learned this part here. Is it that clear? Okay, so this is the point here. And now, if you observe that, the second point I want to discuss here, which is nothing but peak inverse voltage. Peak inverse voltage, or we call it a PIV rating of ब्रिज रेक्टिफाय सर्किट. आता जर तुम्ही आठवलं, थोडासा प्रयत्न केला, तर तुम्हाला पीआयव्ही रेटिंग ऑफ सेंटर टॅप फुल वेव्ह रेक्टिफायर सर्किट काय आहे हो त्याचं पीआयव्ही रेटिंग? वी ऑलरेडी डिस्कस दॅट. कॅन एनीवन रिमेंबर what is the PIV rating of center tap? I say that. Give me response.
2 VM.
It's a 2 VM. Actually, this is the drawback. This is the drawback of center tap because PIV rating is double. But if you observe that the PIV rating of a bridge rectifier circuit as the center tap transformer is not required, so the PIV rating of bridge rectifier circuit is a VM, means maximum voltage appear across the reverse bias diode is a VM. So again, another drawback is overcome in a bridge rectifier circuit. म्हणजे जर तुम्ही कंपॅरेटिव्हली स्टडी केला सेंटर टॅपचा आणि ब्रिज रेक्टिफायर सर्किटचा, तर दोन ड्रॉबॅक ओव्हरकम झालेत ब्रिज रेक्टिफायर सर्किट मध्ये. कोणकोणते दोन ड्रॉबॅक ओव्हरकम झालेत? द फर्स्ट ड्रॉबॅक इज in the bridge rectifier circuit the center tap transformer is not required, and the second drawback is PIV rating of a bridge rectifier circuit is a VM, and in terms of center tap it's a twice VM. So as the drawback of a center tap rectifier circuit is a overcome in the bridge rectifier circuit, and in the bridge rectifier circuit the both the half cycles are used for the rectification, so that out of these three rectifier circuit, half wave, center tap and bridge rectifier circuit, the bridge rectifier circuit is most widely used rectifier circuit, or I say that most popular rectifier circuit is that. Get it my point? So if the question it may ask for MCQ type of a question, out of the half wave, center tap and bridge, which rectifier circuit is most widely used in the electronics field for the rectification, that time your answer should be bridge rectifier circuit is there. Get it my point? So this is the theory behind the half wave, then center tap, and the bridge rectifier circuit is there. Is it that clear? And then we will see that the little bit comparison, between half wave, center tap full wave rectifier circuit, and the bridge rectifier circuit is there. So you can easily give me that comparison. I think we discussed that the few things, and based on that we can write that comparison. How many PN junction diodes are used in a half wave? So it's one. In a center tap, it's a two. In a bridge, it's a four. Is it right? Then what is the second parameter? It's a need. It's a need of center tap transformer. Is the center tap transformer is required for half wave rectifier circuit? Absolutely no. Is the center tap transformer is required for the center tap full wave rectifier circuit? The title itself gives that it is required. And is the center tap transformer is required for bridge rectifier circuit? So it becomes no is there. Then PIV rating. If you see that, what is the PIV rating of half wave rectifier circuit? It's a VM. Then PIV rating of a center tap rectifier circuit is a twice VM. And just now we discussed that the PIV rating of a bridge rectifier circuit, it's a VM. आता हा नंतरचा पार्ट आपण जो काय आहे ते नंतर डिस्कस करणार आहेत. नाउ आय कॅन ट्राय टू राईट इट डाउन हियर. It's a output frequency. Yep, out. If you see that, what is the output frequency of a half wave rectifier circuit? So you can easily say that output frequency of half wave rectifier circuit is the same as the input frequency. Then what about the center tap full wave rectifier circuit? Then its output frequency is double the input frequency. And for bridge rectifier circuit, that output frequency is, again I say that, double that input frequency is there. And now whatever the remaining parameters are there, so for that the derivation part is there. With the help of this derivation for half wave, center tap, and bridge, we can calculate that the VDC, IDC, VRMS, IRMS, rectification efficiency, which is denoted by the eta, and the ripple factor, it can be denoted by the gamma. The certain derivations are there, but for your syllabus, that derivation part is not included, so that if I want to show that, I can show directly the value, because these values are required for the MCQ type of a question. So let me take that another one slide, so that you can directly take the screenshot of it. So all of you, please take the screenshot of it. Okay, and with a little bit change, and that change is, let me write it down here. Then you can take that the screenshot. Let me 1 minute. Let me take this. The rectification efficiency, this is the change here. It's a 69.3%. Okay, this is that. So all of you, please take a screenshot of it and give me the response.
Yes, sir. Taken.
Yes, sir. Taken.
Okay, and I think that I will try to add the ninth one point. Once again, you can take that the screenshot, and that is nothing but output frequency. So here I can write input frequency is equal to output frequency. For center tap full wave rectifier circuit, I say that output frequency is double the input frequency, and for bridge rectifier circuit, I say that again, output frequency is equal to double the input frequency. मग आता जर तुम्ही पॉइंट बघितले तर टोटल 9, then 9 multiplied by 3, it means that total 27 MCQs are formed based on this table. So this table is very, very important as compared to your final MCQ type of exam, online final MCQ type of exam. So please take a screenshot of each. This one is a final screenshot for this comparison. Give me response. Have you taken?
Yes, sir.
Okay.
Yes.
So today we stop here. Okay. And in the next lecture, we will try to see that the capacitor filter circuit, because our filter block is over. As you know that the common drawback of all type of a filter circuit is the output of any type of a filter circuit is not pure DC signal, is the pulsed DC signal, so that we need to connect the output of a filter circuit to the output of a rectifier circuit to the filter circuit to remove that AC component. And in that filter circuit, we will try to discuss the capacitor filter circuit is there. Is it right? Okay, so today we stop here. Thank you.